Chapter 3, starting off here with section 3.1, exponential functions. So here is just a graph of a linear function where t is the input and the output will be the dollar amount. And you can see that the slope is, of course, constant because it's linear. The other graph is that of an exponential function. The slope is not constant, and as time goes by, in this particular example, you can see that this thing begins to skyrocket or grow exponentially. We will see this, in fact, in chapter 4 when we look at the compounding of interest and the effect it has on a principal amount, and also other applications of financial mathematics as well. This is the definition of an exponential function. If you have, f, the function f with x in its domain, set equal to some base that's greater than 0 but not 1, raised to the x power, it's an exponential function. Some basic properties here of the exponential function are now in front of you. Feel free to pause the video and take a look at these. Here are two graphs I created to show the two distinct types of exponential functions. You have what's called exponential growth, where the thing is, as you go from left to right, increasing rapidly. And you also have an exponential decay model. They're both exponential functions, but this one, as you can see, decreases rapidly. Both of them have a horizontal asymptote at y equals 0, or the x-axis. Okay, let's go ahead and get into solving exponential equations. So there's something called the one-to-one property, and that states if you have like bases, then the exponents must be the same. They must be equal. All right, so if we look at our first example, you already have like bases. 7 is, of course, equal to 7. So using our one-to-one property, we're now able to set the two exponents equal to one another and then solve for x. So this one's very quick, very simple. You just get x equals -3/2, and you call it a day. And example number 2, I guess a little more challenging here, but what you need to do in this case is recognize that each of these bases, the 8 and the 1/32, is in fact a power of base 2. So 8 is 2 cubed, exactly the same thing as 2 cubed. And 32, I'll write it this way first, is the same as 2 to the 5th power. So you have to be able to get comfortable with powers of base 2, and then also be comfortable with powers of base 3 and 5 as well. But anyway, going back to this example, at this time, I'm going to go ahead and look at power of a power property. That's going to give us what? 2 to the 3x. And over here, this 1/2 to the +5 is exactly the same as 2 to the -5. That's a definition of a negative exponent. And then again, what I'm going to do is power of a power. So I get 2 to the what? -5x plus 10. And now, finally, I have what? I have a situation where the bases are exactly the same. So now I'm able to let the exponents be equal to one another. So I now have 3x is equal to -5x plus 10. And I just solve for x at this point. So what would you get here? You add 5x to both sides, giving you an 8x equal to 10. You divide both sides by 8. You get 10/8, which of course simplifies to 5/4. And there you go. That's the answer for example number 2. Okay, the third example we're going to look at here in solving exponential equations is one, of course, that looks a little bit different. So what we need to eventually recognize, hopefully sooner than later, that this really has quadratic form to it. Because you have, a 2 in this exponent position, and then a 1 in this exponent position, and then a 0 understood in this exponent position, with respect to the x that's in the exponential spot. So it also contains 3 terms, of course, here. So here's what we're going to do. Let's just use what's called U substitution to figure this out. So in math, you're always allowed to let some variable be equal to some other expression if it helps you solve an equation. So if we let u equal 2 to the x, Do you agree that u to the second power, u squared, would be the same as 2 to the x, what we have above, that's u, squared, which is the same thing as what? 2 to the power of a power, you multiply and you get 2 to the 2x. Well, now look, we have a 2 to the x, excuse me, and we also have a 2 to the 2x now. And look at what they're equal to, u and a u squared. So we can take this information and use it to rewrite this equation, this exponential equation, into specifically a quadratic one that has quadratic form to it. So here we go. So we know u squared is exactly the same as 2 to the 2x. Here is 2 to the 2x. So we have u squared. That takes care of that. And then minus 8. And then what's 2 to the x? 2 to the x, 2 to the x is exactly the same as u. So there's the u. Then you bring down the plus 16, set it equal to 0, and now you can see you have a quadratic equation in terms of u. Keep in mind, you are, in fact, solving for x here, okay, ultimately. At this point, you can go ahead and solve for u, with that being said. So let's see, is this factorable? It sure is. You get the quantity of u minus 4 times the quantity of u minus 4, which means if you set, well, they're identical, but if you set these binomials equal to 0, you get u equals 4, which means what? U equals 4. That's not what we're solving for. Like I said a moment ago, we're solving for x. So let's use this initial equation right here, u equals 2 to the x, to ultimately solve for x. So let's replace u with this 4. So 4 equals what? 2 to the x. Now, this should be a piece of cake. 2 to the what power gives you 4? 2 does. Okay, you can also use the one-to-one property. 4 is a power of base 2. It's 2 squared. Now you have like bases. You're now able to let the exponents be equal to each other. So 2 equals x. Therefore, x equals 2, final answer. So we use u substitution to ultimately rewrite an exponential equation into a quadratic one, which allowed us to ultimately solve for x. Okay, let's look at an application type problem you're going to see in section 3.1. These are going to be easier than the application problems you're going to see in the other two sections, especially in section 3.3. Because in section 3.3, you're going to have to come up with this model based upon given information, okay? In section 3.1, they're going to go ahead and give you the exponential function to use. So we read this question, the number of cell phone subscribers in the United States between the years 2000 and 2010 is approximated by this function, where n of t is measured in millions and t is measured in years, with t equaling 0 corresponding to the year 2000. How many cell phone subscribers were there in the United States in 2000? Well, that would be when t is equal to 0. So the easiest way to solve something like this would be to simply put this function in your calculator, and I've already done that. I just entered that function into my graphing calculator. And then what I'm going to do is what we talked about in class last week. So I'm going to go to my home screen. I like to use vars because then I don't have to worry about my window limits. I mean, I could come up with the window limits so that I could see what I need to see, and then I could trace, whatever t-value I needed to use to come up with the answer. But I just prefer to use y-vars and then ultimately come up with the value of y using that technique. So how many subscribers were there in 2000? That would be when t is equal to 0. That's how you'd enter it in there. And then you would round this value to the nearest tenth. I believe that WebAssign wants you to round this to the nearest tenth. So this would mean 109.5 million people would have a cell phone subscription in the year 2000. And then all I got to do for the year 2012, if the trend continued, how many subscribers were there in 2012? Well, same idea here. You would go to vars, y-vars, y sub 1, and then 2012 would correspond to what? T equaling 12. So you enter in a 12 right there, hit enter, and so now to the nearest tenth, you would have what? 323.0 million people, all right? And here's another way to look at it. That's what I just computed using my calculator. All right, that wraps up the notes for section 3.1. Hope you're doing well. Hope you're having fun. Hope you're staying safe. See you in just a bit in section 3.2.